What specific problem does the proposed method aim to solve in biomanufacturing, particularly regarding the conversion of legacy production records into structured formats?
The proposed method aims to solve the problem of ensuring schema adherence when converting legacy production records into structured digital formats in biomanufacturing. This is critical because any deviation from the predefined schema, such as missing fields or incorrect formats, can violate data integrity standards and lead to compliance issues. The method leverages synthetic data construction and iterative reasoning to guide large language models, LLMs, in producing outputs that strictly conform to the required schema, thereby minimizing the risk of errors. By employing a reasoning-driven approach, the method ensures that the generated records are not only accurate in content, but also precise in format, which is vital for regulatory compliance in the highly regulated biomanufacturing industry. Ultimately, this addresses the challenge of unreliable formatting that undermines trust and complicates the auditing process.
How does the proposed reasoning-driven methodology work? Illustrate it step by step, including the processes of synthetic data construction and iterative reasoning involved in ensuring schema adherence.
The proposed reasoning-driven methodology operates through a series of structured steps aimed at ensuring schema adherence with minimal overhead. First, it involves the construction of a reasoning dataset by creating both synthetic unstructured and structured data using controlled prompts and the Qwen 14b32b model. This dataset is then utilized to reverse engineer how unstructured text maps onto a predefined JSON schema, with the model explicitly detailing the reasoning behind each schema field's population. Next, the methodology employs reinforcement learning, RL, to train a small foundation model, integrating custom reward mechanisms that evaluate schema compliance, fluency, completeness, and correctness. Finally, supervised fine-tuning, SFT, is applied to polish the model's outputs, ensuring they align with real-world standards and are suitable for audit or compliance, thus achieving robust schema adherence throughout the process.
Can you provide a simple illustrative example showcasing how the proposed algorithm translates unstructured text into a structured JSON schema? Please explain the main steps involved with this example.
The proposed algorithm translates unstructured text into a structured JSON schema through a series of methodical steps. First, it utilizes a reasoning-driven methodology where synthetic, unstructured, and structured data are created using controlled prompts. For instance, if the unstructured text describes a product's details, the model engages in a step-by-step reasoning process to map each detail, like name, price, and description, to corresponding fields in a predefined JSON schema. This is achieved by employing a distilled model, such as DeepSeek R1 Qwen 32b, which outputs its chain-of-thought reasoning, ensuring that each schema field is populated correctly. The model is then trained using reinforcement learning with custom rewards that evaluate schema adherence, ensuring that the final output is both accurate and compliant with the required format. Finally, supervised fine-tuning is applied to polish the outputs, anchoring them to real-world examples and ensuring they meet strict audit and compliance standards.
What are the theoretical and practical benefits of using your proposed approach for structured output generation, compared to traditional methods like fine-tuning or prompt engineering?
The proposed approach, which combines reinforcement learning, RL, with synthetic data construction and iterative reasoning, offers both theoretical and practical benefits over traditional methods like fine-tuning or prompt engineering. Theoretically, it instills structured reasoning capabilities within a compact model, ensuring schema adherence with minimal overhead, which contrasts with the resource-intensive nature of fine-tuning large models on specialized data. Practically, this method allows for the generation of outputs that are not only accurate in content, but also precise in format, as evidenced by the strong performance metrics of JSON, which achieved a 41% mean match with only 0.27% noise. Additionally, the use of a reasoning dataset encourages the model to self-check its outputs, reducing the likelihood of random or malformed results, a challenge often faced in prompt engineering. Overall, this approach enhances reliability and efficiency in structured output generation, making it particularly suitable for regulated environments like biomanufacturing.
How was the effectiveness of the proposed method validated? What datasets were used, and what specific metrics were employed to assess its performance?
The effectiveness of the proposed method, think JSON, was validated through evaluation against a structured data extraction benchmark involving 5K rows. The assessment focused on several specific metrics: the number of rows with no output, the number of rows producing valid JSON objects, the mean match percentage indicating the average proportion of fields correctly mapped, and the mean noise percentage reflecting the average proportion of extraneous or malformed tokens within the extracted JSON. Think JSON demonstrated strong results, achieving a 41% mean match, the highest among the evaluated models, and a low mean noise percentage of 27%, indicating minimal extraneous output. In contrast, other models like Original DeepSeek R1 and Gemini 2.0 Flash showed lower mean match percentages and higher noise levels, further underscoring the effectiveness of the structured reasoning approach employed in ThinkJSON.
What notable results were achieved with the proposed method in terms of schema adherence, and how do these results compare with those from other baseline models?
The proposed method, ThinkJSON, achieved a mean match percentage of 41% for correctly mapped fields, which was the highest among the 5 evaluated models. Additionally, it demonstrated a remarkably low mean noise percentage of 27%, indicating minimal extraneous or malformed tokens in the generated JSON outputs. In comparison, the original DeepSeek R1 model had a mean match of 43%, and a higher noise percentage of 11.14%. The distilled variants of DeepSeek R1, Qwen 1.5b and Qwen 7b, performed even worse with high rates of no extracted JSON and significant noise. These results highlight the effectiveness of the structured reasoning approach in ensuring schema adherence, outperforming baseline models in both accuracy and output quality.